So good morning again, everyone. Now we have a bit more participants connected, so I think we can start. If not, it will be too late to conclude the webinar because we have a lot of things to see today on this webinar. So as I said before, today we are going to speak about energy modeling, and Marco Baroni, our expert, will give us the fundamentals and the methods that can be used for starting the work on energy modeling at the country level, but also on other kind of framework. So thank you very much, Marco, to be with us today. And I wish you all a good webinar, and I hope you will enjoy what we are gonna speak about today, and you will learn a lot and ask a lot of questions, because this is what will make the webinar more interactive, and this is what we want to hear, because we want to adapt the content to your needs and try to provide you with the most adapted answers and tools. Thank you very much. I'll give you the floor to Marco, and enjoy.
Thank you very much, Gianluca. I hope you can hear me well. Good morning to everyone. I am very happy to be here today. It's a very important day for me and a very good occasion to show you some basic principles for energy modeling that well, some of them are really general principles and some more of what is being used at the IEA. I apologize as a start because I might say in a number of occasions we at the IEA and so on. I don't work at the IEA anymore. I'm now a consultant at the IEA, but I did work at the IEA for 15 years. So habits are a little bit difficult to pass when you have been saying we at the IEA for so many years. So I hope you will indulge a little bit of the wrong statement that I might use. Also, my apologies. Sometimes I will not be looking at you, but I will be looking there simply because my screen is there. But without further ado, I would like to start today's presentation, because we have a lot of things to look at. With one, I would like to underline one thing that Gianluca said. Interaction is very important. Questions are very important. So please ask any questions you might want to ask during the presentation, ideally with the question and answers part of the that you have, but in Zoom there is the part for Q&A. But also, if you have other ways to ask questions, even by email later on, however you want, the important is that we can have a discussion, because that is why that is what we are there for. So without further ado, I will go and start. Can you see the first slide already? Yes, okay. So today we will discuss energy modeling, and of course energy modeling relies on a number of factors. We will start with the principles. We will of course touch on all the issues of data, importance of data, how we need reliable data, and what is the type of thinking that you put in place for modeling. But before doing all of this, I think it would be very interesting to oops, goes too fast, to start with a question to you. Now you have been using Menti in all the previous presentations, so I think that that now you are very familiar with it. So I would ask you, if you don't mind, to go to on the web page of Menti. Again, if you can see the code, you will need to use the code 503270 to access to access and be able to answer the question. And the first question is a very open one, and it's what you think. We would like to know what you think, what are energy models useful for? The question is very open. You can put any words that you want. The ideal, whenever you see a word that has already appeared, is that you type the same type of word, if that is what you want to say, with the same exact spelling, because that will show the importance of that argument in the overall result. So if you want to start, that would be, I think the floor is open for starting typing whatever you think it's the most important, are the more important elements for you. So sure, we have started very well with energy objectives, energy planning, and explore future. We will wait for some more answers to see. You can put multiple ones, of course. You're not restricted to one. We have planning here. For it's a good example. I mean, energy planning and planning are, of course, very similar. They appear in two different words. Simply because the spelling is not exactly exactly the same. But please feel free to add anything that is important for you and that comes to your mind and what you would like to see explored and answered by the webinar today. We have more. Effective utilization, very interesting and very useful. Energy management program, of course. And we are, I would wait maybe a few more seconds. So if you want to keep adding, please feel free so that we can see more what your energy utilization and effective utilization, perfect. We can see that planning is really the dominant element, but of course, with several other, there are some more answers coming in. Policy developing. That's very interesting. It keeps going. Please keep going as you feel. We will close it in a second, just not to. So we can see how it's the central part, of course, is energy planning, and that is definitely the. But scenario development, utilization, policies, and that is exactly what we're going to talk about today. So we're very happy that that is what you're looking for. So it's excellent. So we go back to the presentation. Again, I will ask you before continuing if you can see the presentation. Just a little wave of Gianluca or Arnaud's head. No, you cannot see the screen. Okay. Let me see. Can you see it now? Yes, perfect. Apologies for these little little breakout times, but of course, doing everything in remote, of course, sometimes have its slowdowns. So the agenda of today. The agenda of today, of course, will focus on four main parts. One is, of course, the general principles that we mentioned about and that are generalities, but very important generalities. There will be 3-4 points that are really essential to keep in mind whenever you're doing any type of modeling effort and exercise. How you build up scenarios. So if you want also the difference between forecasts, scenarios, what type of analysis you can do with models, and then the two big part of any model. We will insist again, and I'm sorry, I will repeat often certain words and certain principles, but because for me, for us, these are very important. And one of these is an energy model would need to look as much as possible at the entirety of the energy system. The more you can look at the overall of the energy system, the more you will be able to understand the relationships, the links, the interactions of the different sectors of the different fuels. Looking in isolation to one technology or one sector often gives you only a partial view of that, and in isolation risks to bring, in particular from policy making, to potentially make policies that are not as effective as they could be if they were considered in the overall of the energy system as a whole. So the two main parts that we will look at is supply and demand modeling, of course. So we can start with the general principles. My apologies, there is a lot of animation, and sometimes I will go throughout it. I will put them on the screen so that you can see them and then talk about some of them. Well, we know about the importance of the energy sector. That is why we're here. So the first point is an obvious statement, an important statement, but an obvious statement. It's energy is at the heart of economic activity, and energy growth and economic growth have in history always gone hand in hand, growing one with the other. Which one contributes to, is the driver for which it's could be a field for debate, but we will not debate that today. Of course, source for economic growth, but also sometimes source for problems. The most obvious one that comes to mind is pollution, and it's not only talking about CO2 emissions, but it's also local pollutants, for example, which is another very, very important aspect, and all the and a number of other aspects that are related to that. Third point, very important, is what I just mentioned 2 minutes ago, is there is no energy island in terms of sector, of fuel, of technology, of country. Because also countries are, from the energy point of view, always related to the others. So understanding how the evolution of all the different fuel sources in relation to the others is extremely important. For example, I have domestic gas resources. I need to understand where the domestic, where the gas demand will come from, if domestic or international, and therefore what possibilities for trade. Very easy example, but very important one in the end. It is very important to understand both short-term and long-term trends. The two can have very different impacts and very different meaning in terms of the way you analyze them, you model them, and what type of solutions you can give to them. But that is one. It's what is short and what is long term is always very subjective in the end. But it's two elements to keep into account. The solutions that can be done in a short time frame, when you don't have the time to transform the system, can be very different from the ones you have in the longer term when you have more time to transform the system, for example. And of course, what are the choices available? What are the technologies available? What are the advantages and disadvantages of each one of them? So when we're coming to energy modeling is how can energy modeling help? Well, it can help on a multitude of levels. The first one, of course, is identifying the links and putting them in a mathematical, well, we use here disciplined way, the relationship between the different parts. Of course, this needs a continuous analysis to be able to understand if these type of interlinks are changing and evolving over time. The second point, of course, is exploring different type of futures and therefore the scenario idea based on different type of assumptions, and so to be able to deal with the obvious fundamental point of modeling, which is there is uncertainty. We need always to remember that any exercise done through a model will be an approximation of reality. Thinking that with a model we can predict reality, in my view, is, let's say, overly ambitious. Let's put it this way. And of course, understanding how the different technologies, the different energy sources can answer the different requirements of the specific part that you are modeling and that you are considering and you are looking into. And this points us to a very important point. There is no model that can answer all questions. Every model is designed, built up with a purpose. And whenever you're building up a model, you should be aware that there are limitations. The way itself, the way you're building it, it will have simplifications because representing reality would require too much. And because of these simplifications, it of course means that there is no model that can answer all questions. So we say no ideal model in this sense. There are strengths and weaknesses of most models that are used, that are developed, that are available. If we look at the IEA ones, so the one used in the World Energy Outlook and the one used in the Energy Technology Perspective publications, this is very much based on economic assessment. So technologies, economics are very much the drivers. You identify what are the promising technologies, what is the impact of policies, what are the potential characteristics, what are the characteristics and the potential barriers for implementation, and how the system can be transformed. So effectively, what options are available. A very important point that I made before, the difference, well, that I touched on before, the difference between scenarios, forecasts, foresights. I can't remember who that was saying it's very difficult to predict, in particular to make predictions, in particular about the future. In the end, we need to understand what type of effort we're trying to make, and this has been often debated and looked in and can be categorized into when you want to predict. So you want to say what will happen in any case, in any circumstance, and that is more related to prophecy or prediction, if we want. Another very important category or family of approach is what will when you're trying to understand what will happen under certain conditions. Conditions. So if a certain policy is implemented, if a certain condition is realized, and then you have forecasts, you have You have scenarios that can be done in different ways. You have foresight. And then, of course, you can have a third family, which is um, what should happen to achieve a certain objective. And the two main examples that I really have in mind is optimization with respect to a function, which is generally cost, but it could be optimization to any parameter that you think that is most relevant for your model. Or backcasting, saying, well, this is where I want to arrive. What do I need to do in order for the system to arrive to that point? So these three differences should always be kept in mind, because often there is too much of a confusion between forecast, scenario approach, optimization. It needs to be always very well kept in mind. So when we are designing a model, there are few elements that are essential, that are very important. I will make a little pause after this slide to allow, if you have any questions, to see if you have any questions. So I hope you will indulge a little bit through this last slide. So one first thing to remember whenever you want to make a model, you need to have data. We will go back on this point enormously. Data are essential to have good models. You don't have good data, it's very difficult to have good models that give you some good answers if you don't have good data to start with. In the IEA, we have the luck, the advantage. You see, I said we, despite the fact that I don't work there anymore. But there is the advantage, the big advantage of having a very important statistic energy data center that provides an enormous amount of data, and yet most often for modeling you need even more data. The more you can find, the more can be collected and used, the more rich will be your model. With one thing to keep in mind, a more complicated and more complex model is not always necessarily better than a simplified model. There is always this balance to keep in mind, to observe between complexity and effectiveness of a model. But still, without reliable data, you don't really go much further. So it's a very fundamental role that historical data play in any model. Of course, when you're designing a model, you need to decide what type of coverage. What type of coverage in terms of sectors, in terms of geographical area. So if you're, of course, looking at your country, you might want to extend and simplify the neighboring countries to understand the trade, if trade plays an important role with them. Energy trade, of course, we're talking about. What type of energy carriers? I mean, can you import gas through which means, or things like these? What type of fuels and potentials are available? Of course, when we're talking about Ethiopia, we're talking about huge hydro potential, but not only. So you need to be aware of what type of coverage, what is your model. We go back to the point of for what do you want to develop your model? How do you want that coverage how do you want to look at the system that you're looking at? Which type of technique? As we said earlier, do you want a bottom-up type of model, so very detailed from the point of view of description of the technologies or the stock that is being used? I'll use a very simple example. I mean, can you have the information about the number of refrigerators that are available in the country and what is their efficiency and their energy consumption, so that you can model and ideally even their age, so that you can model how the evolution of refrigerators will be, or you don't have this information, so you need to use a more top-down approach and use more general type of equations. There are, again, the two are not necessarily better or worse. They can be more or less well adapted to your needs, but you need to choose. If you want to look for optimization, accounting, simulation type. So what type of approach you want to use is extremely important. What type of functions and elements you want to have in the model. So for example, for renewables, very often we're talking about how the costs are decreasing with the technological learning. So do you want to have it within the model, so endogenous to the model, or is it something that is going to come as an external assumption? You want what type of econometric functions you want to use. We will go back to this with few little examples throughout the presentation, but you can have a variety of them. Do you want to have macroeconomic feedbacks? In many models, GDP is an assumption, but then you would need to check if your assumption was if the evolution of the energy world has an impact on your GDP, and if you want to have this feedback and so on. So all of this to get to what type of model design you want to arrive to, what are the boundaries, and effectively what in the model will be endogenous and what will be exogenous, or if you prefer, what will be the assumptions and what will be the calculations done in the model. These are an essential part, an essential feature of models whenever we use it. We want to design them. Sorry. And so the data requirements that we talked, it goes back to the first point. Historical data are very important, but what type of data requirements, of course, depend on what type of model you want to put in place. If you want to detail very much the iron and steel sector, you will need to have quite some information about the production of steel, for example. And with this, before I go on to the next slide, actually, I will stop here 1 second because I do realize that throughout the whole presentation, there will be a lot of information, a lot of things that will come up. So I would like to breathe myself 1 second, but also give you the opportunity to breathe and see if there is any question, although I don't see any. So in that case, I will continue because we really have a lot. And as you can see, I have the tendency to go on quite a lot on each, to describe quite a lot each slide. Okay, I will continue. So maybe this slide and the following one, we will go a little bit faster on them, but very important to remember the differences between the bottom-up and the top-down approach. So the in the end, how you can build depending on the type of data that you have and about the type of objective of your model. Again, I would like to remind one thing: a simplified model sometimes can give you very important answers and can be handled more easily, so to say, than very complex models that require a lot of elements that play one with the other. One thing that I didn't mention that is very important: don't go too detailed on one element and then have one assumption that effectively influences all that detail and makes it a little bit I wouldn't say useless, but less reliable, because that one assumption influences the other parts so greatly. Very important two types of families, in particular in the IEA, where the two publications, the World Energy Outlook and the ETP, is between optimization and simulation. WIO looks at is more a type simulation type of exercise. The ETP has more of an optimization is a more optimization type of exercise, in particular for the power and the industry sector, and it looks really at the optimization from the point of view of course, the economics point of view, using the times model. So when we look at energy, the families of energy models, we mentioned top-down and bottom-up type of models, but we need also to remember what type of, if we have forecasting or strategic planning type of requirements and visions that we need to fulfill, and then start identifying where the different model that we want to create will be, and which type of answers will be more suited to be answered by that type of model. Again, the type of model that you design is very dependent on the type of the answers that you want to get out of it. With this, we have finished the part on the general principles. Before going to the scenario building, I would again stop 1 second. Otherwise, we will go to the next, if I remember correctly, the next Menti question. I don't see questions, so I will continue. If you don't stop me, I continue. So the next Menti question, we would ask you again to go to the web page, to the menti.com, please, and to look at the next question that I don't see on the screen. And yes, it's coming. Perfect. I hope that you all can see. Just a reminder that you always, if you had already the code, you just need to go to the next question. Otherwise, you need always to remember the 503270 number to access it. And so the question, in your opinion, is sorry. The question is, in your opinion, what are the main elements to consider when developing an energy model? So we go back to what is the model objective, what is the quality of data. I mean, if it is more important, the objective, the quality of data, the political trajectories, the assumptions, the timeliness of input data. Remembering they're all important elements. There is no right or wrong answer, but we would like to know what your opinion is in between what is more important and what is less important among these elements. So we start seeing the first.
Just jumping in for a second, Marco, yes. Since I see that there is some text in French. Sorry, we forgot to translate that. So value 1 is not at all. I totally disagree. And if you give value number 5, I totally agree.
Many thanks. I didn't even notice it. So all my thanks for that. It's funny how the brain works. I read it and I didn't see it. It's very funny. So as we mentioned, all of these elements are important, but it's always very, I think, important to know what your opinion is about the weight, the relative weight of each one of these elements. We have few answers. We will wait for a couple more maybe before continuing. also because, as Gianluca mentioned at the very start, the presentation today is a little bit longer. We have also one Excel exercise short that we would like to go through, so a number of elements to look into. So quality of data input seems to be the winner, and I agree that that is essential. Also, I have to say that I worked for many years in the World Energy Outlook team, and so I was a big user of data, but also I worked for several years at the beginning in the energy data center. So also the relevance and importance of statistics I have started with how important it is to collect, to provide good data, and how those are important for, well, you have seen it very well with Gianluca and the other colleagues in the previous presentations. For me, it's one of the most important elements. Model objective, I completely agree, is another very important element. Don't build a model and then say, oh, but I want to answer that other question. Well, it's not so obvious.
Hi, Marco. Can we go with the two next Mentimeter questions so we will save the time to reconnect to Mentimeter later?
Yes, if you want. If you want, yes.
Let's do that so you can go a bit faster.
Yes, yes, sorry. As you can see, I'm a little bit, it takes me a bit of time to go through the different slides and different points that I want to make. So we will re-mention this, but maybe we ask it now, as Gianluca is suggesting. It's a very good idea, and it's we will come about this very soon. But in your opinion, what energy prices are the most useful for? Again, no right or wrong answer, but do they are they useful more to determine? Oops. Okay, they have disappeared. Do you see still the questions? Because I don't. Okay. Sorry, I'm just seeing the results and not the questions anymore. Because I admit I haven't connected myself to Menti. I should have. So for the time being, we have 3 answers. Again, the answers are all correct because affordability is one of the most important elements that any policymaker looks at. Trade, of course, is affected strongly by energy prices. Investments, if you don't have enough, if the prices are not enough high enough to trigger investments, will not happen. And of course, they are as a result of supply and demand. So all the ones that I'm seeing at the moment are all correct. Again, maybe we wait for 1 or 2 more and then we move.
In the meantime, Marco, we have a question.
Yes, I didn't see it, sorry.
From Mr. Allegen. And the question is about how do we verify that our modeling is correct, and what are the softwares that we can use to verification and validation of models?
Now, the very good question. How to first? There is a big difference between if you are developing the model yourself or if you are effectively buying a software that has already certain features in. If you're buying it, normally it has been, well, depends who and what you're buying, but it has been validated by a number of usage and previous people. But let's say that you're developing it. The first thing to validate it with is, of course, testing with what has happened in the past under the circumstances that have already happened, and also understand the more the expertise, the more you will see that certain results are correct or incorrect through any model. What I find extremely useful, of course, is looking at literature and understanding what type of equations, what type of approaches, and what type of results you get from different models from important institutions. Of course, I'm talking about the IEA because we're here today, but there are several institutions and universities that provide very important important models and very useful to compare with. The softwares for verification and validation, I would say there is a part that is a little bit of more of an art, if you want, in understanding if the results that you're obtaining are correct or not. But my apologies, this is a little bit disturbing. But you could use softwares in the sense of simple verifications of the results. You could use more complex softwares to compare, for example, the type of approaches and the type of equations used. It depends again if you're developing it yourself or if you're buying it, because in that second case you will not have much access. I would stop the Mentimeter here and go to the next one. Thank you very much. You were perfect. So in your opinion, what are the main drivers and of future energy demand trends? Technology development, GDP growth, population growth, energy access, low carbon energy policies. So energy policies, and in particular the low carbon ones. Again, all of these very important elements, again, we would like to see what your opinion is about. So we're starting, of course, with GDP and population growth, which I would agree are two of the most important basic drivers in any projection. Not to say that the other three elements are not important. They are all important. But we've put them here exactly because they are so important. Okay, if you want to add one, you can also choose one, more than one answer if you want. So yes, GDP and population growth are, I think, the most important ones in terms of basic drivers, and the weight of the two will also depend much on what type of country we're looking at. So, for example, in more advanced economies, population growth has a much smaller role than GDP growth. In African countries, I would say that both elements are extremely important. Technology development, of course, has a very important element, because the transformation that we have seen, for example, of and the drop of costs of solar PV and wind technologies has been really significant in the last 10-15 years. With this, I would like to thank you and maybe go back to the presentation, because I do realize that I am going a bit slower than I wanted to. So can you see my screen again? Perfect. Thank you so much. So we were talking about the second part of the building scenarios. Now, again, some magic words that I like a lot, and when we're talking about models, this is coherency. Coherency for me is one of the basic elements that need to characterize any model. You cannot have, I don't know, global demand of gas or of oil that drops 30% from one scenario to the other, and the relative prices that increase 30%. The two things are unrelated. Little example, but just to say the coherency between the elements, the trends, the economic, the relative economics of the different technologies, and the policies put in place is extremely, extremely important. Of course, as we mentioned, building scenarios is very important to look at how the different policies can influence the different patterns. If you look at the scenarios of the World Energy Outlook, how we always call in short the WEO, well, it's the current policy scenario is just a basic standard business as usual. It's just setting a baseline. Is really not used. The stated policy scenario is the policies under consideration today, and where those policies with the normal technological development would bring the different countries. The sustainable development scenarios, the 1.5 to 2 degrees, so the below 2 degrees scenario, but matching it with air quality and energy access goals. So a very important scenario that joins together a number of important SDG, well, not important, fundamental, I would say, from the energy perspective, SDG goals. The Africa case that has been developed, my apologies, last year or 2 years ago. And time goes by too fast. I apologize. And that is a very important scenario that is that has been developed for Africa to look at the possible strategic pathway to reach the 2063 agenda. Very important scenario for Africa to show what can be do and what can be really achieved and how to achieve it in the different African countries. I think I was not in the WEO anymore when this was done, and I found it extremely, extremely interesting and insightful. So you can create a number of scenarios or cases. Cases are generally part of a scenario where you change one part of the assumptions, not the entirety. And that's why you see scenario, scenario, scenario case. And in this case, excuse me for the double word, the Africa case is a very important and insightful one. So as I mentioned, you can create scenarios, cases, or also look at the sensitivities of the different within the different ones. Now we will go through today a lot of the World Energy Model, which is the model used to create the World Energy Outlook projections. One important thing to say: we talk about this model because, of course, it's the IEA organizing this series of webinars. But these principles can be applied to most models. So I would encourage to think about this as, yes, it's the IEA that is doing this, but these are all the basic principles and all the approaches that can be used in any model. So to approach it with a much wider approach than just that one model. Nonetheless, all the structure and so on will refer to the World Energy Model. So in the World Energy Model, we have, can you see my, my mouse, or shall I use the pointer of, yeah, you can see it. So we have a number of assumptions The most important ones are socio-economic drivers, GDP, population, and so on, as we mentioned. A number of technological drivers, for example, the cost of a number of technologies in the future. Certain are endogenous, like the renewable ones. And very important, a number of policies, like eventual CO2 policies, but all the different energy policies that are considered in the different countries. And there are three main parts. The final demand part, we will go back to each one of these, so I will just sketch them out. The end user demand, the final energy demand part, the transformation of energy, where the biggest part is held by power and heat, power generation and heat production, but it of course has also all the part on refineries, on coal transformation, and so on. All of this to give us the total primary energy demand. That, of course, as mentioned in one of the previous Mentimeter with the prices, needs to be balanced between demand and supply, of course, through trade, but very important through the energy prices. So this just to show that all the things that we have been looking at are interrelated and are all important. And these two parts that we're seeing here are one of the fundamental parts of the model. You need to keep in balance supply and demand. How do you do that? Through prices and through trade. The three things are all interrelated. So, sorry, I didn't mention one thing. And of course, you have a number of results, which are all the energy flows and projections, also not only energy, but CO2, and very important about investments. Now, we mentioned assumptions at the beginning, and assumptions are a very important part. There is historical data and there is assumptions that are needed, and all of these need to be validated through consultation with other and are in the IEA validated through consultation with other institutions and through peer review literature, through a number of sources. And I think that this part links also very importantly with the group that is being created through this capacity building exercise of relating the energy experts in the African countries with the experts in the IEA and beyond, because these relationships are always very important. You want to validate an idea, an assumption, a point. You have a contact point to have a relationship with, and that is extremely important. Costs, of course, in these type of models are very important and are being peer reviewed very regularly, and in particular for the technologies that evolve very rapidly. We go back again to the renewable ones, but not only. And it's very important to review them with all the relevant stakeholders, but I would say that academia, institutions, and industry are extremely important. And of course, in the case of the IEA, is also making available the transparency about all these elements, all these assumptions, is always very important. The IEA and ETP are peer reviewed by hundreds of experts. Now, when we're talking about exogenous assumptions, as we mentioned earlier, we're talking, of course, about population. My apologies, 1 second. By population, GDP, value added by sector, gross national income, all different aspects. The energy policies all the targets, the type of standards of support measures, the way they are implemented or not implemented, if they are ambitions or they have effective um, policies to implement the different targets, the evolution of energy access that of course is extremely important in a number of countries in the world. In Africa, this of course is with significant differences across the different countries extremely important. If there is carbon pricing or not, if there are subsidies for different energy sources. The technology cost assumptions, as I mentioned before, is not only about investment cost, but also efficiencies, cost of capital, and so on. But as I mentioned before, the assumptions can be assumptions for certain technologies and instead endogenous, like the technological learning for renewables in the WEM model, in the World Energy Model. And of course, the development of infrastructure that can have an extreme high impact on the development. When we're talking, for example, about energy access, we're talking about on-grid access, small grids, so mini grids, or off-grids type of applications, and what is their evolution going to be throughout time. So can you develop an off-grid today that then will be connected to a mini grid, and then in X years to be connected on grid. So all these type of evolutions are very important, and so the infrastructure development can play an extremely important role. So we mentioned, of course, access. When we're talking about access, we're talking about, on one side, clean cooking, and on the other one, electricity. I will mention the importance of it, but I will not stop too long here, because we will mention both of these graphs, if I remember correctly, in the webinar 6 and 7. Correct me if I'm saying the wrong numbers. The one on biomass and the one on off-grid, on electricity access. So, of course, the importance of how and the speed for full access of the different sources can have a significant impact on the energy trends. But anyway, it's a variable that needs to be considered very deeply in the different models. This is the Mentimeter question that we went through on energy prices. So I would now go to supply modeling, unless there is any other questions. So
it's Marco, maybe we can take the opportunity to answer one question that came from Yusuf Abdul related to energy access and to the scenario. So the question from Yusuf Abdul was, should we have a single Africa case scenario considering the level of energy access in North Africa compared to Sub-Saharan Africa? So this is a very good question, and if we see the chart, the figure that Marco just threw, we can see indeed that the situations amongst different African regions are very different. But to answer the question, maybe I can explain a bit more how the Africa case is built. So this scenario is under a normative approach. So the idea is to say by 2030, we want to have reached certain objectives. And there are three of those objectives. First is economical growth, as was defined in the 2063 Africa Union agenda. The second objective is related to energy access and reaching universal access of both clean cooking and electricity in all regions. And again, you can see that it's North Africa are much more advanced as compared to other. And the third objective is related to emissions and to pollutions. So this scenario is built under those different objectives that do not apply in the same way to all regions. And the way it was built was that 11 individual countries have been modeled like individually, and Ethiopia is one of them. So we have results and projections specific to Ethiopia, and Gianluca has shared in the WhatsApp group some presentation of those results, and all the other countries were modeled as another region, and North Africa was also a different region. So to make a short answer to your question, Yusuf and Marco, feel free to build on that. We aim to take into consideration regional differences and to have consistent modeling amongst different countries.
That is an excellent point. Thanks a lot, Arnaud. I'm sorry I didn't see this question. It's an excellent point. So often graphs that you see will be aggregation of different elements and different countries. But most often what is the aim is to provide the more detail, the highest detail possible in all the different projections. Of course, again, that famous balance that we were talking about in between the level of complexity and how much you can look deep into detail, and then creating eventually homogeneous clusters of countries. So if you have countries with similar electrification rate and similar policies on the on reaching universal access with similar characteristics, then you can eventually put them in the same pool. But generally, the best approach is to do one country individually, and therefore the 11 countries that Arnaud mentioned. I would go to the supply part. I apologize, because otherwise I'm afraid of going too far beyond the time that was allocated for this. So when we're looking at supply, so why are we starting with supply? Before I mentioned demand transformation to get, final demand transformation total demand to have supply. The reason to have supply was, again, to stress the importance of energy prices as a link between supply and demand. But in the end, you need to start from somewhere in that loop, because we go back to the idea, the energy system is a whole. So when you want to look at it, well, you need to choose a point where to start from, and then it's a circle. And you will see that the presentation is made exactly in this type of loop idea. So if we're looking at supply, we're really talking about production and trade, and the impact of energy prices on their trends. Now, of course, when we're looking at fossil fuel prices, is what we were mentioned and what were indicated in the Mentimeter question. The fossil fuel price needs to be sufficient to trigger new investments. If the price is not high enough, well, then new investment will not be there to satisfy demand. So if you have a certain level of demand and the price is too low, investments will not come, supply will not be there, there will be an imbalance. So you need to raise, so the price needs to be higher, demand will be lower depending on what the elasticity to the price is of the different sectors and uses. And the investment, there will be the possibility of investing in more fields, because more fields that will become profitable will come there. And this is an exercise, if you want, it's an iteration exercise that will bring the two parts in balance. So very important for investments. It is, of course, to be remembered that this type of modeling exercise look at the overall trend. So the type of modeling like the WIO one looks at the overall trend of the resources, doesn't look at the possible fluctuations and variations that you can have on a monthly, weekly, daily, hourly fluctuation of prices basis, which instead, for example, would be very important if you were running a trading type of business. If you're trading energy, that is the essential part, so the type of model would be completely different. While when you're looking at these type of modeling exercises, what you want to have as an idea is the overall level of the average price throughout, generally throughout every year. That is but could be also seasonal. Depends depends on which fuel we're looking at. So these are the resulting prices for the three main scenarios of the World Energy Outlook, with this idea that I mentioned of finding the balance between supply and demand. So using the price to find the right level of demand that can match of supply that can match demand through the investment in new projects. And this is another way of showing it, adding one element. Of course, this is an element that we will find in all sectors. Whatever you have today has a lifetime. In this case, we're talking about the production of oil wells, but it could be I don't know, the lifetime of power plants, the lifetime of air conditioning units, the lifetime of refrigerators. It's the lifetime of any equipment has an equipment. So generally you have the amount, in this case, that is being produced today, the profile that so how that production of today will decrease over time. You know what the demand that you want to satisfy is, and for each year, what type of new investment, so new capacity, needs to come online every year. And that is one of the fundamental exercises done in the supply part, and it's looking at what is the difference every year, and so how much new capacity, production capacity, needs to come online, how much new oil production, oil in this case, but this can be applied to gas, to coal, to all the sources, needs to come online every year. This was an example, of course, of supply, not to of crude oil supply. Not to forget that there is a very important part that relates to the refined products. The World Energy Model, being a world model, needs to have in balance all the flows of refined products in the world. Again, it depends what type of model you're looking at. I'm sorry, I repeat this point enormously, but this is one of the very fundamental points. If you're creating the model for your country, then what you need to understand is, for example, if the refinery that you have or that you don't have is needed or is not needed, depending on what the international prices are and what the import or export capabilities are, or what the import or export or what the import dependency you want, the policymakers want to have. In the WEM, in the World Energy Model, of course, all these elements need to be in balance through the crude oil market, but also for the refined products. We already looked at this many questions, so I will go straight to the demand modeling. Again, each section stopping 1 second, not too long, not too to allow more time for later, but I don't see other questions, so I will continue. Okay, so We mentioned supply and demand, and now without scaring you too much, but demand, of course, has a lot of different parts. We will go through, again, some general principles, and the main three end user sectors and the power sector. So if we're looking again at the schematic of the overall model that we were saying, that we were showing already a couple of times, the end user, the final sectors are the main ones are industry, transport, buildings that includes both residential and services, and agriculture, although agriculture in most countries is important, can be extremely important from the economic point of view, but as an energy user is generally the one that is much smaller than the other three. So that is why we will concentrate on industry, transport, and buildings. The demand part, of course, includes then the transformation. We will focus on power and well, on power generation really to get the total of primary energy demand, as we mentioned earlier. So if we're looking at the demand side, these are the sectors that we mentioned, and the representation of the different sectors really changes depending on the needs and the availability of data. Again, some magic words: availability of data, importance of data, reliability of data. That is extremely important. And so each sector has its different drivers, its different purposes, its different availability of data. So each one needs to follow a certain logic that we will see is common in many aspects to all of them, but that requires very different data sets, very different type of approaches in some cases. So in some cases, it's very important to understand, for example, what is the stock, as we mentioned, of refrigerators, but it could be of any other type of home appliance. What are the capacities for new sales and so on? I'm thinking about cars, for example. What is the lifetime of each equipment? Because the lifetime of a refrigerator, of course, is not the same lifetime of a coal power plant or even more a hydropower plant. What are costs and efficiencies of each one of these elements is very important. Of course, ideally for the historical data is to have the data. There are also techniques to estimate them, and we will go back to the idea, maybe not today, we will not go back to that today, but more in the in-country, more in detail modeling, on how to estimate them by similar type of clusters. You can approximate the data from one country where you have the data to one, or one sector or one element where you have the data to the one where you don't. This structure applies to all final sectors, and it's, I think, probably the most important thing to remember when we're talking about the final sectors. And it's remembering that it's a mixture of bottom-up and top-down approach, that you need to consider three main levels, three main elements. One is, what is the type of drivers in your sector? The last one is what you want to obtain is how you will obtain the projections of your final energy demand. One is, the third one is what is the energy service that you want to satisfy. So if we're talking about lighting, we're talking about what is, well, the unit is lumen, but what is the type of light that you want to have in a certain place. If you're talking about the air conditioning, you're talking about what is the level of, what is the temperature that you can have in the apartment. The same thing, of course, in cold areas applies to space heating, and so on and so forth. So it's what is the driver for, sorry, let me, oops, what is the driver for what energy service, and how do I get from that to the final energy demand throughout the different technology choices and efficiency levels. So this is really the core of final demand modeling, which is, with all the differences among the sectors, as a type of thinking, very applicable to all of them. What I wanted to show you is then a small Excel exercise that let me show. Apologies, I need to find it. So in this case, can you see the Excel exercise? Yes, fantastic. So I will enlarge it a little bit. We will have a few Excel exercises throughout these webinars and much more during the in-country ones. And we have tried to structure them in similar ways. You will recognize little features in all of them. And in particular, the historical parts, the historical data, with hiding some of the columns just to make it more visible, and the projections, which in the end is the ultimate effort and the ultimate goal of these type of exercises, again with hiding years in between, with the different elements that are being looked at in the different rows. So in this case, and most often there is a little bit of color coding between the historical and the projections, units and parameters that are being used for the calculations for the projections. This is a little bit the structure that you will see now, and that I will show you at the end of today's presentation for an exercise that we will look again. But again, to mimic, to show what I meant in that previous slide, drivers, useful energy, final energy through efficiency, I jumped a little bit over the technology allocation through cost and which one you're choosing. And it's not done in this exercise as well, because it adds complication. And for the sake of time, we wanted to keep things simple. But you will surely recognize. Can you see the screen? Is it large enough, or shall I enlarge it a little bit more? Is it better like this?
You can enlarge it. Yes, that's better.
It's better? Okay. Sorry, again, the visually it's always better. So we always start from historical data. Historical data, in this case, of course, what are the main drivers and what are the important drivers? My apologies, I forgot to say a very important thing. In this case, we will look at the development of energy demand for air conditioning, and how this, in a very simplified way in this exercise, can be approached and estimated. So of course we start from the basic socioeconomic drivers, GDP or GDP per capita, of course, and population, the number of households in a country, the number of AC units. Now remember that these numbers are somehow true and somehow invented. They are, I didn't have all the data to prepare it, but they should be in more or less a ballpark. So my apologies if there are imperfections and data that are not correct. The service demand intensity, which is, and I will come back to in a second what this means. There. And what is the historical electricity demand for this use. So these are the typical historical data that we need, and again, the importance of having them reliable. In the same block, I included the assumptions. We mentioned so much about assumptions and assumptions of the main socio-economic drivers, so of GDP and population. The second step in that flow chart that you have seen in the previous slide, if you remember, was going through an econometric analysis. And the econometric analysis is used to estimate the future evolution of a number of important drivers. In this case, and I will not spend so much time, but I wanted to show you how to get to the evolution of number of households and number of air conditioning units per household through two different type of functions. The two very, very simple econometric approaches. One is simply a function of this type, so a divided x to the power of c plus b, with the parameters being here, and the error being calculated in row 17, where these are the historical data that we mentioned about, and this would be the continued evolution as a function of GDP per capita. The other one is simply using the inbuilt charts and the trend lines of Excel. So you take the historical data of AC units as a function per GDP per capita. You look at, in this case, a linear trend was very much well fitting. You have your elements, and you build the projections. So the projections of econometric of the number of households using these A, B, and C elements, you will see, sorry, using these three elements, or the one of AC units, will use these two different approaches. What I want to say with these two examples, it's a very, in reality, generic and simple thing. And it's whenever you're using an econometric approach, you need to identify what the best type of function fitting your drivers and your results is. It could be as simple as a linear function, as we just saw in this case. It could be a little bit of a more complex formula, like in this case, or I saw the question, I will come back to that in a second, or it could be, and that is used in a number of cases, the penetration of appliances in the system, which often follow an S-curve. And again, we will go back to this more complex one in the in-country training. But what I meant with this is just to say, whenever you're using this approach, remember that you need to first analyze what type of function can better fit the type of element that you are estimating. I saw a question about the error sum and how that is used. If you are familiar with the use of Excel and the use of the solver in Excel, so under data, you can have the solver one. What you can do once you have your formula, so effectively, Y is the household occupancy and X is the GDP per capita. You build, you build a formula using those three elements and GDP per capita, those three variables and GDP per capita, to create your your approximation formula, your approximation of the historical data. And once you have done that, you look at the error formula, which is simply the difference of the two elements, the real historical plus the estimated historical to the power of 2, and you sum them up. And with the solver, you minimize the sum of all these elements by changing these elements. So for example, I will change all of these 3 elements to 1, and you will see that now the formula went completely wrong. So you can't even see it here anymore because it went completely off the chart. So you build your error, your function that you want to create as similar as possible to the historical data. The error is simply the difference of the 2 to the power of 2, and you sum it. With the solver, you will want to set the objective, which is this. Oops, excuse me, I repeated it twice. You will want to set, okay, why is this not working anymore? Okay, the error sum to the minimum value, ideally to 0, by changing the cells, these 3. And if you solve it, you will go back to that error sum that we used to have. So this was a way to estimate these future evolution as a function of GDP per capita. Gianluca, sorry, you wanted to reply and I didn't see it. No? No, it's okay. Was the explanation enough, or do you want me to go through that again, Girma? In absence of answer,
I think it's okay, Marco. We can go to these more technical Excel things on another time.
So once you have obtained your through your econometric analysis, of course, what you want to estimate is the total service demand in time. Your total service demand. You remember in that flow chart, drivers, service demand, and electricity, in this case, demand. Well, what you have as the data to start with most often is how many kilowatt hour you are of service you are providing per appliance, for each AC unit, for each air conditioning unit, which could be, I could have left flat. I made it grow over time, assuming that the new ones will provide more, but this could have been flat eventually. And therefore, the total service demand will be the product of that number that we saw up, so the kilowatt hour of service per appliance, times the number of units for the past and for the projections. Through the evolution of efficiency, we will then obtain the electricity demand. Now, the evolution of the efficiency level, here I have put it completely arbitrary, growing by 1% per year. But in reality, this would be a result of the technology and cost-based approach. So the more you have type of technologies that can compete, which most likely will have some that will be more costly and more efficient, the more you will be able to transform the system towards a more efficient one. So change these assumptions. In this case, that I didn't want to go to that level of complexity, I simply chose to grow the energy efficiency by 1% per year. But this will be a critical element that will depend on on the different technologies that you have available. If you have only one, of course, the efficiency will follow the evolution of that one technology. I hope the example was clear enough. Of course, we will show it with you, and we will be happy to reply to any questions that you might have. Now I will go back to the presentation. Can you see the screen of the presentation? Yes. Okay. Perfect. So just before continuing, I will go to the previous slide and just reminding you what we just saw. Drivers, econometric analysis, total useful energy, jumped over these. Through the efficiency levels, we had the future final energy demand. In this case, future electricity energy demand, because it was talking about air conditioners being run by electricity. And so with different strategies, you can build different scenarios. And when you see these type of graphs, you effectively have the sum of all the different sectors of all the different, you have the different sectors. In this case, it's for the globe, which means it's the sum of all the different countries, for all the different fuels and the evolution, of course, of the different fuels and of the CO2 intensity in this case. Sorry, of the total CO2, not the CO2 intensity, of the total CO2 emissions. So very important elements to take into account when we're doing final energy demand final energy demand modeling. I see that it's quite late. My apologies. It will take at least another half an hour, I'm afraid. These models can be used for a variety of purposes. One is very important, of course, what we just mentioned, and it's what is the evolution of the energy trends. One is how much of the equipments will need to be replaced at what pace. This is a part that I didn't mention. It was in the previous slide in the graph at the bottom. But of course, of today's, actually I will show it because it goes very quick, and it's here. We mentioned it for the production of oil, but of course that is true for any technology. You're retiring old technologies, so also the energy demand related to those ones is decreasing. And each year you need to match an amount that is the increase of new demand, but also the replacement of the old one. And so going back to this first part here, it's how much do I need to change of the equipment, at what pace, and how changing this pace can change the future evolution of trends through different policies. That is linked, of course, as well. What is the demand for the different sectors, but mainly, again, what is the influence of energy policies on these trends, which is, of course, the very important element that we want to answer. And what is the resulting investments, CO2 emissions, and so on. I see, I will, before continuing, sorry, I'm seeing two questions. The elements that I used in the parameters were calculated sorry, the question is where these parameters were coming from, and those are calculated by Excel. And the example ax plus b, x is the variable, A and B are constant and are estimated by the graph, by the inbuilt graph of Excel, but it could be estimated through the same technique of the solver, and you would get the same results. It's just two ways to get to the same result. I will go maybe a bit quick through the industry sector because I would like to spend a bit more time on buildings and transport that I think are a bit more important. But of course, when we're talking about industry, we're also talking about energy, non-energy use. So, for example, production of plastics. And the main industries that are more energy intensive, like iron and steel, cement, chemicals, paper, pulp and paper, and so on. So, of course, the activity variables in this case will be much more related to the production of these goods, so the production of aluminum, of steel, of chemicals, of cement, of paper. And another, of course, very important activity variable will be the value added of the industry. And generally is these six subsectors that we are looking at in the IEA, they are looking now, in the IEA, because these are the most energy intensive ones. One example that is very important in my view is the importance of energy efficiency in industry and in motors in particular. So when you're looking at the industry sector, you can see how relevant is the importance of motor-driven systems and how the efficiency of these systems are going to affect enormously the trends in the industry sector. As I said, a little bit quick on industry, my apologies, but then it's a bit more in my view, important to go a little bit to transport and residential and buildings. So when we're looking at transport, we can really look at the two main things: the transport of persons and the transport of goods. And when we're talking about the two, we will stop 1 second for our next Mentimeter. If I can ask that to be put on. Thank you very much. So you should be able to go always with the same code to the next question. And the question is, what in your opinion is the most important variables among the ones proposed for to model energy demand in passenger road transport? Again, you could have passenger or freight road transport. You can always answer to more than one questions. Is just to see which is your opinion. Remembering again that same issue about French. This is I don't agree, and I agree fully. So in between the variable passenger kilometer, the number of cars, how many kilometers per car, and what is the number of passengers per each car. Again, all of these elements are important. They're all used. We will see it. Actually, you will see it, because I can anticipate maybe while we're looking at this that we will propose you to we will propose some exercises for the next webinar, and the one about there are, Gianluca, correct me, 2 about statistics, 2, and 1 about modeling. The one about modeling will be exactly about transport modeling. So you will see more of these elements in the modeling exercise. And we're seeing that for the time passenger kilometer and actually number of cars and passenger kilometers are the two winners in the race. We have already 10 people that replied, so I think we can proceed. Again, the answer is all of them are important. The variable passenger kilometer is the one that is most often used, at least in the IEA, but also a lot in literature, because is the one that expresses better the how much you're transporting, how many people for how many kilometers. You will also see it in the exercise for next time. Can we go back? I will go back to the presentation. Oops, what did I do? I'm sorry, I was maybe doing something wrong. Now we should be able to continue. So when we were talking about transport, as we mentioned, we always have the same structure, is the assumptions, what are the main activity variables. In this case, we use the most passenger kilometers and ton kilometers for passengers and for transport of goods. And of course, with different equations, with different approaches, with different relevance, according to the different sectors that are being looked at, with road transport being the one that is detailed more in detail for both passenger and ton, but of course aviation, rail, navigation, and other playing a very important role and being modeled explicitly. This is what we were mentioning about the road transport, an example. So the vehicle fleet times the distance traveled and the car occupancy, similar element that you use to obtain the ton kilometers. This, of course.
Sorry, Marco, to jump in. If you go back to previous slides, so we had a question from Adi Salem. What is the importance of number of passenger per car? So you can see that number of passenger per car or occupation is one of the parameter to calculate the passenger kilometer parameter.
Thank you very much. I'm sorry, I sometimes are missing some of these questions. I haven't seen this one either, so my apologies for that. So thank you very much for answering it. So all of these are the general principles. Then you do your model, you make all the calculations, and of course then you need to present these results. And that's why we are often presenting you some of these graphs that of course put together all this information. And one of the difficulties sometimes is to simplify all this enormous amount of information in representations that are simple and straight to be seen and represented. Now, this slide is about the importance of the growth of electric cars. As you know, in a number of countries, electric cars are being looked at, are being in several cases also subsidized and pushed to push the transformation. But one of the very important elements that I think is to be taken into account is how the different parts we mentioned how the energy system is an interlinked one. Well, of course, this is a very important part of the evolution of the sector. But if you look at the impact on the oil demand, well, passenger cars effectively contribute decrease a bit the oil demand, but of this decrease, much of the decrease is not due to the increasing fleet of electric cars, but it's a lot due to the efficiency of the new, so the evolution of the efficiency of cars. So the new cars being more efficient, they consume less, less petrol, and if I remember correctly, 60% of this decrease, or if you prefer, twice as much as the impact of the electric cars, is what is the importance of efficiency in the consumption of oil for cars. So the importance of efficiency is extremely high, and the transformation and the related policies for the transformation of the system is as important as the transformation of the fleet itself. But if you look at the overall of oil demand, well, passenger cars, you could almost say that it's flat, or anyway, a bit decreasing, with much of the increase coming from trucks, aviation, and shipping, other two sectors that we just saw, and the increase of oil demand in plastics. Again, this to put what we just saw about the road transport for passengers, so the passenger cars with respect to the electric vehicles, to the efficiency of new cars, and with respect to the oil demand in this case in the world. So it's a global figure. When we're talking about vehicle ownership, of course, we're talking about extreme differences depending on what country we look at. We go back to the Africa outlook and the Africa case that has been developed last year by the IEA, and we can see how already within Africa the differences of ownership, what is today and what is the evolution over time is very different from country to country, with of course very important impacts on the energy trends. And the energy trends can of course then change dramatically depending on how the ownership, so the amount, the vehicle stock will evolve in each country. With this, I would go to the building sector again a little bit quickly, but still not too quickly because I don't want to leave behind some. So my apologies for the delay of today's presentation, but I think that it's important to fix some important elements that we have been looking at. So again, buildings being this, the residential and the services sector, I think much of the following slides will be about the residential sector, but most of what we are going to say applies also to the services sector. Again, the same structure. Drivers, so assumptions and historical data. Activity variables, most of the important ones are floor space, the number of households, the appliance ownership for each type of appliance, and in the case of the service sector, the service sector value added. There are 6 main sectors being looked at, space heating and cooling, depending on what country we're looking at. If it is in cold temperatures or in warm temperatures, or that have the need for both. Water heating, of course, sanitary uses in houses. The needs for cooking. We will come back about this part in particular when talking about biomass in webinar 6. Correct me if I'm saying something wrong. The lighting needs and uses, of course, and the appliances one, which is of course a very general sector and has a lot of detail for a number of different appliances. The more you can have information about the stocks, the more you can be have more of a bottom-up approach and be able to be a bit more accurate in the projections of each one of these sectors. So we go back again to data. Data being an essential part of all of these models, but the building model really needs a lot of detailed data for all of those sectors that we mentioned about. Like all the others, that instead is a general one, is technology, policy, and cost data, but also indicators are very important and useful for the projections in this sector, and again with different subsectors and different importance and different drivers for the different subsectors. I will insist very quickly on one thing. Sometimes some data are not available, but can be estimated through certain techniques. But this we have decided to leave out of today's presentation, but it's a very important one. We have two quick Menti questions if we want to go through them, or shall I jump on them? I'm just asking to my colleagues if for the sake of time we do them, or we can do them. We have the time.
Let's do them very quickly, so
okay,
we can finalize the webinar.
Thank you very much. So the first question is about if we have, it's about air conditioning. We've seen it in the example, but if we have the energy consumption of an AC unit, what is the most important parameter in your view to estimate total demand? Is more floor surface or the number of households? Again, let's remember always what is the driver. In this case, is an AC unit. I will just wait a few more answers. Again, both important ones. Okay, we have 8. Let's see if we have another couple, and then we proceed. 9. One last one, maybe. Okay, I would close it here. So we are more or less one-to-one. The answer actually in this case was the floor surface, and you might have been taken a little bit off-road by the example that I showed, because I was actually using the number of households, because the number that we had there was of AC units per household. And not the number of AC units. In this case, if you have the consumption of an AC unit, you need the floor surface, because the bigger the house is, the more AC units you will use. If we can go maybe to the next one. In this case, what is the most important driver for water heating in a household to estimate energy demand? Is more floor surface or the occupancy of the household? And I think that in this case, we don't really need to wait much more, because number of the occupancy is winning by far. And of course, that is the right answer, meaning that you will need more water heater the more people you have in the apartment, quite regardless of how big the apartment is. is more the number of people that are present in the apartment. So that is perfect. Thank you very much. So that was absolutely correct. We will go back to the presentation to go towards the final slides. We should have only few. It's only the power sector really missing. Before getting to the final to the power sector, of course, a couple of words on similar graphs to what we've seen for the transport sector, for example, is the general ones at the beginning is the trends that you can obtain in different scenarios depending on the different evolution of the energy sources and of mainly of the policy assumption of the policies that you want to implement. So going from the stated policy scenario to the sustainable development scenario with the very significant changes in the way the energy is used, so energy efficiency, which energy is used, so the transformation of the mix, and the impact on CO2 emissions. A very, very important element, and that is why we really talked about the AC units a couple of times, is of course the growing need of air conditioning and what is expected to, and the importance that is expected to play in Africa in the future. Of course, Africa, we know very well the need, the temperature of Africa, and the future need for cooling can be well estimated. Well estimated can be broadly or well estimated. Depends what level of uncertainty you want to assume to attribute to it. But there is no doubt that the growth of air conditioning, of energy demand for air conditioning will play a very important role in future trends in Africa. And therefore, looking at these trends, not only from the point of view of the total energy demand, but as much of this is, as this is talking about electricity demand, it's not only about the total electricity demand, it's also about how the profile during the day of the energy demand will change, and therefore what impact it will have on the power system, on the requirement of the power system, and the amount of power capacity that will be needed in the system. We go back to the links between the different sectors, the evolution of the different sectors, the links of among them. So in the Africa case, the evolution of the residential cooling demand is, if I remember correctly, it was more than 20, it was something like 15 or 20 times by 2040 than today. No, I'm just trying to, anyway, going, increasing extremely significantly in the order of one order of magnitude or more. Of course, this can be moderated. This huge increase can be moderated, effectively be cut in half through greater efficiency. So we go back to the importance of energy efficiency in the different elements, and you have seen that we have seen in the previous slides between the stated policy scenario and the sustainable development scenario, how the difference of the total amount of energy was very significant. This can play an enormous role in the demand for cooling demand. Final words about the power sector. When we have the demand from the final sectors of electricity, that electricity demand needs to be matched by the supply in the power generation sector. Power generation sector has effectively two central points. I will not go too much into details about them, also because that is one of the areas that I know quite well, but I will not spend too much time about. But there are two things always to remember. Electricity cannot be stored in huge quantities, which means what is needed is what you need to produce in that moment. And there are two central elements to any power system. One is how you operate the plants that you have in that moment, let's say in that hour, in that week, in that year that you're considering. And how do you evolve? So how do you change? How do you add new plants? So those are the two central points: how you operate, how you add new plants. So how you operate and how you add. You start with electricity demand. You obtain the load curve, which means the hourly profile. Generally, is used the hourly profile of demand. This will be used in both the way you use the plants and the way you add the plants. So what type of new plants you need. You have a number of assumptions. We go back always to this idea of assumptions, calculations, results. So here in different colors, we have the assumptions, you have the calculations, you have the results. Very important to know. For power generation, as we saw for the supply part before for fossil fuels, electricity are in the end a result and a balancing point between supply and demand. So there is a feedback of electricity prices into demand, and through the end user prices. I should have added unless local subsidies exist, but that I thought that this schematic was sufficiently complicated as it is. Maybe a special word about the renewable sources, where of all the things that we said before, there are two things to remember. There are additional, that are obvious if you want, but that need to be mentioned. One is, what is the potential of that source? So the potential of hydro and other renewables, because we always talk about hydro in Ethiopia, but of course there are many other renewables that are available in Ethiopia. So what is the potential, and what is the need for eventual subsidies to get certain renewables started? In the world, this has worked extremely well, for example, for solar PV, when the cost 15 years ago was very high, and thanks to the deployment, the cost of solar panels have come down enormously. With this, I would like to conclude simply because remembering the close of the loop. So the sum of final demand plus the energy transformed gives you total primary energy demand, and that needs to go in balance, excuse me, with supply. We go back to the loop and we close the energy system as we talked about till now. I would maybe go, so this concludes the presentation. I would maybe spend just 3 more words about the exercise for next week for modeling, if this is possible. Gianluca, Arnaud,
maybe you can just introduce 2 minutes what is about the exercise.
Okay.
Because in any case, we will see it on Wednesday more in detail.
Perfect.
This is Sardinia.
Yes, that is definitely Sardinia. That is totally Sardinia. It's my screensaver. My apologies. So I wanted to not show you necessarily Sardinia, but to put the exercise. My apologies. Can you see it now? Yes, perfect. So this is the exercise that you, the modeling part. You will receive also the two on statistics, as we mentioned. But it's just to explain it and go very quickly through it. Again, as we mentioned, structure is the same as the one that we just saw, historical projections with the hidden years. We will ask you several questions, 1, 2, 3, 4, 5, if I remember. No, there is a sixth one that you will be able to see. And it's about the evolution of oil demand in a fictitious country throughout time, through to 2030, given the characteristics of the system, the historical ones that we talked about, and the evolution of population as exogenous assumption, as we mentioned in the previous example. So the aim is to calculate the different questions of asked in the exercise, and it's about virtual, effectively, the passenger vehicle, sorry, the passenger kilometer, my apologies, indicator, my apologies, it was not coming, the passenger vehicle indicator that we were talking about, and arriving then to the energy demand projection and the impact on import dependency in a world that is a very simplified oil world. And this very simplified world is what is effectively written up here. We are assuming that oil is being consumed only in the transport sector and only gasoline cars exist. So it's a very simplified system. It's overly simplified if you want, but again, it's just to be able to calculate these different elements in a very simplified world where oil is being consumed only in transport, only in gasoline cars. I think that this is really explaining it. I mean, the rest are just the questions. Do you want to give any more details? I'm just looking at my colleagues.
I think it's okay like that for the moment. They will receive the exercise, and Wednesday we will really go through that during 1 hour and also. I think we are okay for today. It's even perfect. Almost. It's already lunchtime in Ethiopia, so it's better we.
Yes. So my apologies for the delay. I thank you all, and I would like to stop here and give back the floor to Gianluca and Arno.
So thank you very much, Marco. This was a really, really comprehensive and important presentation. We have seen a lot of concepts. We are all learning. So that is very good. We also enjoyed all your questions. And of course, if you have others, please send an email, a WhatsApp text, and we'll try to give you all the information we can provide you with. Say that, we will send you today or tomorrow early the presentation that Marco provided today. We'll send you this exercise to be solved if you have time by Wednesday. And we'll send you also the exercise that Marco showed on air conditioning. So you will have also the Excel file to play and maybe to find better answers to your questions. Say that, we'll also be able to share with you all these videos of the webinars that are now online. So we'll share our link with you once I also put online these webinars from today. So we'll have a kind of a complete set, and we'll continue uploading the videos as the webinars goes on. So what is next? Next, we are going to have a webinar on Wednesday at 10 o'clock at this time. It will be a shorter webinar because we'll be solving only the exercises that you received last week on energy statistics. So the 2 exercises plus the exercise that you just see on the screen that Marco introduces today. So please, if you have the time, take a look at least at exercises and try to think on how you will solve them. And if you have more time, try also to do the calculation and solve them completely. On Wednesday, Arnaud, myself, and also Marco, if he's available, will walk you through the solution of the exercises, and we'll have some question and answers related to all the webinars you already had. So please write down all your questions and bring them on Wednesday. And the last session will be just the day after, on Thursday. We'll speak about interesting topics that has been introduced today as well. And this is the use of solid biofuels, or wood, charcoal, etc., for mainly cooking in the residential sector. And we'll see what are the data issues with that, what are the other socioeconomic impacts. And also we'll speak about the other interesting topic, that is electricity access, sorry. So thank you very much again. And I hope we'll keep in touch on emails and